but we're improving. And I think our speakers tonight will have a great understanding of exactly how to improve the processing and throughput of transactions on the blockchain. The Bitcoin blockchain can process about 7 transactions a second. Now, just as a point of comparison, Visa and MasterCard can process globally 65,000 transactions a second. So we've got a long way to go. But, we're getting there, and we're at one of those turning points on the blockchain here in 2018, where the universe is telling us it's the time for that technology to revolutionize our lives. And there was another moment, there have been many moments in history when that is the case. And the one that we can think of here tonight is back in the 17th century, Newton and Leibniz came up in the same year with calculus. Calculus, which transformed our technology, transformed our science. And funnily enough, the debate in the air in Europe was there, and they were able at the same time to come up with this astonishingly complex notion of how to measure the curve the slope of a curve, and that transformed our whole means of producing mathematical equations. Now, we're in that same moment today. These two gentlemen, Philipp and Mustafa, have come up with an application for a technology called sharding to the blockchain. Now, who here knows what sharding is? Okay, cool. So that's about maybe a third, quarter. So sharding essentially is a database management technique from like normal databases, and although blockchain is a sort of fancy, decentralized database, we can still think of it in database terms. And sharding allows you to keep multiple copies with some redundancies on your network. But essentially, what we're seeing with the blockchain at the moment is, with those low transaction figures I mentioned before, a lack of the ability to not have, say, 20,000 Bitcoin nodes validating every single transaction you make. So sharding, we could define as splitting up the state of the blockchain system into multiple streams acting in parallel rather than a single serial chain, which, because it allows you to process transactions in parallel, allows you to process a lot more of them at the same time. So it's that moment when techniques and elements of other kinds of technologies are ripe for coming and bringing them on board with the blockchain. This is what the gentlemen who are here tonight will be discussing. Anyway, so now first we have Philipp Jovanovic of OmniLedger. Philipp's a cryptographer and a postdoctoral researcher at the Swiss Federal Institute of Technology in Lausanne. His research interests include applied cryptography, information security, and decentralized systems. Philipp is a member of the Initiative for Cryptocurrencies and Contracts, IC3, and a scientific advisor to the Dfinity project. And I think he will be up first, although, as I recall, I think first we've got a music video. I think we have, we're going to see a little element of what the Moscow conference was like. Now, that's going to come up about now. Yeah, boom. Anyway, that was the Moscow event, and here is Philipp.
So let's see if that works. Is the signal? Ah, great. Okay. So welcome everyone. Thank you for the introduction. It's a real pleasure to be here. And today I will present you one of our latest research projects, which is called OmniLedger. And OmniLedger is a secure scale-out decentralized ledger. Before I start, however, I want to talk briefly about my co-authors, because this project is, of course, not just a development of my own, but of many other people without whom this would have never been possible. So at this point, thanks to Lefteris, Nicolas, Linus, Eva, and Brian, who all contributed significantly to this project. So my talk will have four points. First of all, I will go through a little bit of motivation to motivate the problem. Then I will introduce the OmniLedger design. I will present you the evaluation of our prototype implementation, and then finally I will conclude my talk. All right. So, as most of you probably know, the Nakamoto consensus mechanism was the technological contribution that enables Bitcoin's breakthrough. Thanks to its simplicity, it was also adopted quickly by other distributed ledger systems or altcoins. However, it also has several drawbacks, which I want to recap here briefly. So, first of all, it has quite a significant transaction confirmation delay, which means when you as a client send a transaction to the Bitcoin network, then it takes at least 10 minutes until it's being confirmed, because that's the amount of time it takes to produce a new block and include a new transaction. It also provides only weak consistency, meaning that you're not really certain that your transaction is actually included in a block and committed to until you wait for at least 1 hour, because that's the time it takes until you have produced 6 blocks, and the probability that there still are changes in the end of the blockchain, so-called forks, is then very low. So you have to wait at least 1 hour. It also has quite low throughput, as we've already heard. It provides roughly 7 transactions per second in Bitcoin. And then there is the very, very wasteful proof of work mining that wastes huge amounts of energy. So addressing these challenges is really crucial to move towards cryptocurrencies that can operate efficiently on a global scale. So when I want to pay, for example, for a coffee with my Bitcoins, then I don't want to wait for 1 hour until the transaction is really confirmed, until I can get my coffee, right? So, and as Lorenzo already mentioned, there was one recent example that really highlights how critical or severe the issue has become. So we all know that people on the internet love cats. And now that they also love blockchains, it was only a matter of time until somebody came along and combines the two. So there was a company who developed this game that lets you breed and trade cats on the Ethereum blockchain. And this was this within a very short amount of time got a lot of popularity. And it resulted in that the complete Ethereum network was completely jammed up. So, although this is kind of a stupid example, right? It shows, nevertheless, how critical the situation is. If we ever want to deploy a large-scale applications on top of distributed ledger networks, we really need to get to a point where we have large-scale on-chain scaling. So, however, the situation is not that easy, right? You cannot just go in and throw more hardware on Bitcoin or Ethereum and then hope that your system scales. So, there were quite a few attempts already on how to scale distributed ledger systems, and I want to also recap that a little bit here. So there are three crucial properties that you want to have from a distributed ledger system, which are security, decentralization, and scale out. And I will present a few systems that are on different angles of this triangle. So first of all, there is Elastico, which was presented at the CCS academic conference in 2016 in a paper called A Secure Sharding Protocol for Open Blockchains. So Elastico does sharding by looking at the proof of work, and it checks the least significant bits and then assigns, according to these bits, the blocks to, or the transactions to certain miners. However, the problem is that this is not a bias-resistant approach. You can just drop blocks and that thereby influence which miners see which transactions or which blocks. Another problem of Elastico is that the validators, they constantly switch shards and forces them to, and it also forces them to store the entire global state, which for a high throughput system is a bad property, because in a high throughput system, your blockchain will increase very, very significantly within a short amount of time. Since Elastico also relies on proof of work, it has a very high transaction confirmation latency, and when you do the math, you actually realize that the failure probability of the specific shards is very high. So for one shard, it is around 2.7%. Under a 25% adversary, and when you scale that up and you do the math, for example, for 16 shards, then this leads to a 97% failure probability. And you don't want to use a system that has a 97% failure probability. And also, Elastico does not really provide atomic cross-shard transactions. That means you cannot send, if you have like accounts in two different shards, then you cannot send a transaction from one shard to the other. But this is also a property that you want to have. The next system is called, that is on the scale out and security axis, is called centrally banked cryptocurrencies and was presented at NDSS 2016. And as the name already suggests, the specific use case of this system was in a permissioned environment and for banks. And it makes use of a trusted source of randomness for sharding and auditing. And it also has no BFT consensus mechanism. It only uses a simpler two-phase commit protocol. More importantly, also in RS coin, you have to assume you have to trust your clients, that your client is not misbehaving. Otherwise, a colluding client and a validator, they might be able to double spend. Then on the axis of security and decentralization is Bitcoin. That's one of our own works, which was presented in the Enhancing Bitcoin Security and Performance with Strong Consistency via Collective Signing. And that was presented at Usenik Security in 2016. So Bitcoin allows you to do or implements a very efficient and secure consensus mechanism. However, Bitcoin cannot scale out. So at a certain point, you cannot add more hardware and achieve even more performance, because that's there are technical limitations in the consensus mechanism of Bitcoin. So what I want to talk about here is about OmniLedger, and I will show you that this system achieves all of the three properties. But to start, I wanna introduce a small example. Namely a strawman design, which we call Simple Ledger, and we will use that as a running example throughout the talk, and I will show you how you can transform Simple Ledger into OmniLedger. So Simple Ledger evolves in epochs, and it has a trusted randomness beacon that at the beginning of an epoch always produces a random value. And then the validators in the system, they take this random value and they compute their shard assignment based on that value. So why are we doing that? Because the shards will be much smaller than the overall population of the validators. However, there is a certain ratio that between malicious and honest validators in the overall population. And by randomly assigning our validators to the shards, we ensure that this ratio is also maintained within the shard. So by that, we prevent that an adversary can select certain shards and put his malicious validators into that shard and thereby break the security guarantees of that shard. So once the validators have been assigned, they bootstrap from the shard ledger, and then they start processing transactions through a consensus mechanism such as Bitcoin. However, simple ledger has several drawbacks. Namely, there are three security drawbacks. First of all, the randomness beacon is a trusted third party. Then there is also no transaction processing during the validator reassignment, because the validators at the beginning of every epoch, they are assigned to new shards, and the probability that a validator, since this is a randomized process, that a validator goes to a new shard is very high. So basically, from an observing point of view, during these reconfiguration, the entire system halts until the validators have reassigned themselves and rebootstrapped from the shard state. And then also, Simple Ledger does not provide any cross-shard transaction support. There are also several performance drawbacks. One of them is the Bitcoin failure mode, which when something goes wrong in the Bitcoin consensus mechanism, there are certain fallback mechanisms that have a bad outcome on the performance. Then there are high storage and bootstrapping costs, as I already mentioned. If you have a high throughput system, then your blockchain will increase or grow very quickly. And then there is also a throughput versus latency trade-off, meaning that you can either have big blocks and which give you a lot of throughput, but then to propagate these big blocks, it takes a certain amount of time, which reduces your latency, or you can have the other way around, that you have like small blocks, good latency, but a bad throughput. All right. So now that we have set the stage, I want to go to the main part of the talk and introduce OmniLedger. So first of all, OmniLedger, I want to talk about the design goals of OmniLedger. So we have three specific security goals that we want to achieve with it. Namely, first of all, full decentralization. We don't want to have any trusted third parties or single points of failure. Then we want to have shard robustness, which means that the shards process transactions correctly and continuously, even if there are some reconfiguration events. And we also want to have secure transactions throughout the lifetime of the system, meaning that the transactions commit atomically or abort eventually. We also have three performance goals, namely the first one is the scale-out property, that says that the throughput increases linearly in the number of active validators. That means if I add more hardware to the system, my performance also gets better. Then there is low storage, saying that the validators do not need to store the entire shard transaction history. And there is a low latency, that transactions are confirmed quickly. So we don't want to have this throughput versus latency trade-off. So with that in mind, I will show you how to transform Simple Ledger in 6 steps into OmniLedger. First of all, I will introduce an approach that allows you to do sharding using distributed randomness. Then I will talk about selective validator reassignment, which gives us this robust epoch transitions. Then I will introduce the so-called atomics protocol, which does client-managed atomic cross-shard transactions. And then I introduce 3 performance improvements, namely, first of all, Bitcoin X, which is a more robust BFT consensus mechanism than Bitcoin. That is specifically tuned to the use case in OmniLedger. Then I will also introduce shard ledger pruning, that means which will drastically reduce the storage and bootstrapping costs. And I will introduce a mechanism which we call trust but verify validation that removes this throughput versus latency trade-off. Okay, so let's first come to the security properties. So the first one is the secure shard validator assignment. So to recall, the challenge here is that we want to prevent that an adaptive adversary is able to subvert an entire shard with a very high probability. And how we do that already in Simple Ledger is that we use randomness to distribute the validators evenly across the shard, to maintain the ratio between malicious and honest validators also within the shard. So, and how we do that here is we first have, that's a three-step process. First of all, we use a verifiable random function-based approach to run a lottery across all the validators to elect a temporary leader. So this is the red node here in the first step. And then once this leader is elected, he will coordinate a protocol which is called RandHound that we developed, which allows you to generate this publicly verifiable distributed randomness as an output. And then once that's done, all of the validator can take this random value to which they also contributed, verify that it was created in a benign way, and then from that value they can compute their own shard assignment, and that's then the step 3. So, and through this approach we use that at the beginning of every epoch to periodically reassign the validator to shards. So, which brings us to the next problem, that in simple ledger we always switch out or we have no control over which validators go from one shard to the next, because we assume that there is a full validator reassignment and bootstrapping which enforces that the system holds during these epoch transitions. And to solve that problem is that we specify a swap out batch size, which is like this k value here, which is below 1/3 of the shard size. And then we again use the randomness that we generated to compute the permutation of the validators within the shard, and then we only swap out the first k of the validators and distribute them evenly across the other shards, and thereby we maintain the shard sizes and also the ratio between malicious and honest validators with very high probability. And then the 2/3 remaining validators within the shard, they still continue running the BFT consensus mechanism, and they ensure the security and the liveness of the shard. So the next problem the next challenge that we want to tackle is how can we send transactions from one shard to another? And we want to do these cross-shard transactions in a way so that they commit atomically or abort eventually. And what we introduce here is the so-called Atomics protocol, which is a client-managed protocol. So, and when you have a look here at the example on the right-hand side, how this works is a client, he specifies first his transaction that he wants to do. For example, here he has, let's say, 2 accounts, shards 1 and 2, the blue and the green one, and he wants to credit an account in the 3rd shard, which is the orange one. And then the client specifies this transaction and sends it to the input shards and waits for confirmations from the input shards saying that, okay, we locked your funds that you want to credit to the 3rd account. When this is successful, the client can collect all these proofs, go to the output shard and say, hey, look, the funds were frozen, you can credit now the target account. If one of the input shards returns an error, which is the lower part of this graphic on the right-hand side, then the client can take, of course, he cannot then credit the final account, but he can use the error message to go back to the successful input shards and reclaim his inputs because there was no transaction, right? So there must be a mechanism so that the client can reclaim its inputs. So the Atomics protocol ensures enables these cross-shard transactions, and it assumes optimistically that the client is live, right? Because the client sends a transaction and he has actually an interest to see the transaction go through. However, even if the client goes down, once he has broadcast the transaction to the network, any other node in the network can come along and finish the transaction for the client. So it's only crucial that the client sets up the initial transaction, which is anyway something that the client wants to do, and then he can actually go offline and let the system handle the rest. So these were the 3 security improvements from simple ledger towards OmniLedger. And now I want to talk about performance improvements. The first one is the BisCoinX consensus mechanism, which is used within the shards to maintain consensus. It's a variant of Bitcoin, and what it does is it trades off some scalability for a higher fault tolerance. So it uses a group communication pattern instead of a tree communication pattern. Tree communication gives you very high scalability, but it's also very fragile. And what we realized when we were doing this is that for the configurations that we were considering, namely up to 600 nodes per shard, the Bitcoin X mechanism actually performs better than the original tree-based Bitcoin. Only once you go past a certain threshold, in this case it's actually these 600 nodes, the regular Bitcoin tree-based communication is better than this group-based communication. And what we additionally use is a block DAG instead of a blockchain within the as the data structure, because it captures the dependencies between the transactions in a better way that better utilize the available resources, which gives you an improvement of the throughput and the latency actually. The next improvement, or the next challenge that we want to tackle, is the high storage and bootstrapping cost for validators in high throughput system. And how we do that is we also go back to a very old trick from computer science, where we summarize the state of a shard in so-called state blocks at the end of an epoch, and then run a consensus on that. And as soon as the consensus is established, the validators who join in the next epoch can just bootstrap from that particular state block, because the consensus mechanism ensures the consistency and integrity of that block and thereby of the entire shard. Which means that the new validators, they don't have to like replay the entire history as it is, for example, now in Bitcoin. If you spin up a new full node, then it takes quite some time until the full node has validated the entire history of Bitcoin. And this then, as a consequence, so this shard ledger pruning drastically reduces the storage and bootstrap cost. All right, so this brings me to the last technical and performance contribution of OmniLedger, which is the trust but verified transaction validation. And this tackles the challenge of this latency versus throughput trade-off that I mentioned earlier, that you can have either big blocks and get good throughput, or you have small blocks and get good latency. So, and how we do that is that we split the validators within a shard into a core validator set, and then a set or several sets of optimistic validators. And all of the transactions, they first go through the optimistic validators, and they can very briefly check if the transaction is good, and then send feedback back to the client saying, okay, I optimistically validated your transaction and everything seems to be fine. And then they batch these transactions into blocks and forward these to the core validators, which batch them into even bigger blocks and then revalidate everything that it's good. And only once that's done, the block actually goes into the blockchain. So consider a client who just wants to, for example, pay his coffee, which is a very low value transaction. He basically can just say, okay, I trust the optimistic validators that they did their job well, and then I can go ahead and just pay for my coffee. On the other hand, if I have a high value transaction, I want to wait until the core validators, I can spend some more time and wait until the core validators have actually revalidated this transaction and that we're sure that the consistency is good. So by this two-step approach, we like break or remove this trade-off and get both good low latency and a high throughput, as we will see in a moment. Okay, so this brings me to the end of the design section, and now I want to talk a little bit more about the evaluation of our prototype. So we implemented OmniLedger in Go, and together also with all the sub-protocols like Bitcoin Hex, Atomics, or the randomness generation process. And all of those implementations are based on the DIDIS code. So DIDIS is our lab. And we have there the Kyber crypto library, we have a network library called ONET, and we have the so-called Authority framework. Authority stands for collective authority, which encapsulates all the protocols, such as, for example, Bitcoin or Atomics. And you can see all the code online on github.com/ds. So, and the setup that we ran this on is a system called DetaLab, where you can rent several physical machines. And in our example, we rented 48 physical machines. They all had Intel Xeon processors, 24 gigabytes of RAM, and 10 gigabits per second network links. And to simulate a more realistic network environment, we restricted the bandwidth to 20 megabits per second and a 20 millisecond round trip latency. The first property that we looked at was, or the first thing that we evaluated was the throughput. So here you can see a graphic on the x-axis. It shows the shard size and the adversarial power that we assumed. And on the y-axis, you see the transactions per second that the system achieves. So for example, when you take the third column, where we have shards of size 70, so we have 70 validators within a shard, and an adversary who has roughly 12.5% of the validators under his control. Then we achieve with this OmniLedger trust but verify approach, this is the blue bar, we roughly achieve 13,000 transactions per second, which is like Visa. I also printed the Visa throughput, which does on average 4,000 transactions per second. So with that configuration, you already get like 3 times the throughput of Visa. Of course, at peak times, Visa can do way more. Like, for example, if you have a Black Friday sale or something like that, then they do the 50K transactions per second. But the average throughput is roughly like 4,000 transactions per second. And if you have a more powerful adversary, which is the bars on the right-hand side, then you, for example, 25%, then you need shards up to a size of 600, and then you still get a throughput of more than 1,000 in this configuration with 1,800 validators. So the next thing that I want to show you is that OmniLedger is really able to scale out, meaning that when you add more hardware and more validators, then the throughput really increases linearly. So in this configuration, we assumed a shard size of 70 and 12.5% adversary. If you only have one shard, then in this configuration, you get roughly 440 transactions per second. And then if you add more shards, 2, 4, 8, or 16, then you see that the throughput also doubles with each step, right? You go from 400 to 800 to 1,600 to 3,200 and so on. So then the final property that we also evaluated is the latency, to show you that we can get rid of this latency versus throughput trade-off. And here again on the right-hand side in the configuration where we have a 25% adversary and 600 nodes within one shard, when you just do the regular validation, then, and you have 1 megabyte blocks, then the latency that you get a confirmation, right, you send a transaction and you get the confirmation back is roughly 14 seconds. And when you move to this 2-step validation approach, that gives you a higher throughput because you can manage bigger blocks. Then the first level validation, you get a feedback within 4 seconds, which is good for just low value transactions like paying a coffee. But if you have a more high value transaction and you want to be really sure that your transaction goes through, let's say you, for example, want to buy a car or something like that, then you can also wait the 60 seconds it takes until the core validators have revalidated the transaction and appended it to the blockchain. All right, so this brings me to the to the end of my talk, and I want to conclude. So I've presented you OmniLedger, which is a secure scale-out distributed ledger framework. It allows to do secure shard validator assignment via this public randomness generation using the Randown protocol. It has support for client-managed cross-shard transactions using this Atomics protocol. Inside the shards, we run the Bitcoin X consensus mechanism, which is a very robust and very performant consensus algorithm. I also showed you that thanks to sharding, you can actually achieve in public blockchains Visa level throughput and beyond. And thanks to this trust but verify validation, we could also get rid of the latency versus throughput trade-off. A thing that I didn't mention so far is that OmniLedger is it's a framework, and you can actually use it with proof of work, with proof of stake, in a permission setting, or any other identity establishing mechanism that you wish. The paper is available online on the IACR ePrint archive under the depicted link, and it will be published later this year at IEEE Security and Privacy. And many of the code fragments that we used for evaluation of our OmniLedger prototype are available on github.com/days. All right, so that's it from my side. Thank you for your attention. We have questions later, right?
That's right.
Okay.
Thank you, Philip. That was fascinating, technical, and very specific. To the audience, what did you understand? Did you get that? Was it clear? Was it crisp? Did it have a punchy conclusion? Yeah? Yes? Yes. Okay. So now we'll have a little competition for both OmniLedger and Chainspace. We want you to come up with the best strapline, like to tell us and to tell the world what these things do that you can this evening. So we're going to, during our fireside chat later, we're going to take a little poll and see if we can come up with a good strapline. Currently we've got, Philip came up with OmniLedger, a secure, scaled out, distributed ledger framework. Now, maybe we'll start with that. My version was this. Now, I don't know, Philip, if you think this is any good. We'll find out now. OmniLedger. Everything on the blockchain. It's as fast as Visa. I don't know if that will sort of also take some elements of the concept forward for you. Anyway, we'll start with that. And now, 1 second. Just got to get my notes. Now we move on. So in our joust, well, is it a collaboration or is it a competition? We'll see. We have another view of sharding, which has been very ably explained by Philip, from our second speaker, Mustafa Al-Bassam of Chainspace. Mustafa is a PhD researcher at the Information Security Research Group of the Department of Computer Science at UCL, University College London, where his research interests include the intersections of peer-to-peer systems, distributed ledgers, and information security. He's also an advisor to Cognosec, an information security services company. He should know, because this, friends, is the Frank Abagnale of the blockchain world. He is a former black hat hacker who could crack your crypto wallet, who could get your mother's maiden name and find out all that you can do on the net. But he's gone straight, and he's come and started doing research for the blockchain revolution. Well, welcome to the great Mustafa Al-Bassam. Mustafa.
Thank you for that wonderful introduction. If you just give me a minute to set up my slides.
in the meantime, while we get that set up, I just wanted to make you aware that of the crypto news today. So I don't know if you're looking at Cointelegraph or any of the Bitcoin newspapers, but Warren Buffett, second in command, a 94-year-old businessman at Berkshire Hathaway, who said that Bitcoin is evil and should be stamped on by the Americans. Now, the one thing you do know about anybody who appears in the media, look at Jamie Dimon recently, who's backtracked on his notion that he would fire any of his employees who bought or invested in Bitcoin. The coalition of people who are undermining Bitcoin and blockchain in the press are, if you realize, those who are already invested in it, because they want people like us to be angry with them and invest even more. So look at the stories behind the news. Crypto is very much in the public eye. And with that, we have Mustafa with Chainspace. Everybody, Chainspace. Give them a round of applause.
Okay, so I'm going to be presenting Chainspace, which is a research project done with my colleagues Alberto, Bano, Dave, and George. Alberto, Dave, and George are actually here in this room, so you can talk to them after if you want to talk to them. And so Chainspace is a project that actually is trying to solve a similar problem to OmniLedger, but with a different solution. So the motivations are similar, that blockchains aren't very scalable, and CryptoKitties pretty much demolished the Ethereum network. So if a cat game can destroy the Ethereum network, then we obviously need to come up with better scalability solutions. But the second motivation is that blockchains are intended to be transparent by design. So that means that every single transaction that you publish on the blockchain, everyone can see it, because everyone needs to see it in order to validate it. So if you want to have more confidential transactions or do more confidential things on the blockchain using secret data or data that you don't want to share with the world, then that's not very good. So we have two contributions here. The first contribution is that Chainspace aims to be a scalable smart contract platform. And the second contribution is that we intend to support what's called privacy-enhancing technologies by design to allow people to create smart contracts on the blockchain that don't require users to have to reveal sensitive information about themselves. So I'm going to go through an overview of Chainspace, and then I'm going to talk about how we achieve privacy by design. Then I'm going to talk about sharding and scalability, and then I'm going to be talking about what are the security properties we achieve. And finally, I'm going to talk about performance of the system. So, quick overview. How does Chainspace work? So, on a fundamental level, in Chainspace, everything can be represented as an object. So an object can, for example, be anything from a bank account, or a hotel room, or a train seat. So smart contracts, or all the code on the blockchain operates on these objects. And these objects can be in one of three states. They can either be active, inactive, or they don't exist. So to give you an example of what could be an object, so let's suppose you have a wallet contract or a bank account contract. Let's suppose Alice has a wallet with a balance of 10. Alice's wallet is an object. So at that point in time, there's an object that represents Alice's wallet with 10 coins inside of it. Then let's suppose Alice wants to make a transaction from her wallet and pay someone 5 coins. So she might make that transaction, and that changes the state of her wallet. She will obviously have 5 less coins than she had. So what that does, essentially, in Chainspace, that creates a new wallet object and makes the previous wallet object inactive. So you can see that underneath this object, it says that object 1 becomes inactive, and then the object 2 goes from non-existent to active. So all smart contracts do in our system is they change the state of objects. They create new objects, and they make previously active created objects inactive. And the key point is that only active objects can actually be used in transactions. So that means that once Alice's wallet, original wallet with 10 coins inside of it, becomes inactive, no one else can make a transaction from that object, because then that would mean that Alice could spend her coins twice, which is obviously not something that we want to do. Another example is a train seat booking system or a train seat booking contract. Let's suppose that you have an object that represents a train seat that's free. It's unbooked. And let's suppose Alice wants to go ahead and reserve that train seat. Alice uses the smart contract to publish a transaction on the blockchain to take that active free train seat object and then create a new object that represents a taken train seat reserved by Alice, and obviously the free version of that train seat becomes inactive and no one else can reserve that train seat anymore. So in a nutshell, that's how objects work. And in our system, we have nodes, which are basically like miners in Bitcoin, and these nodes are responsible for receiving transactions from users and processing them and adding them to the blockchain, just like any other blockchain system might work. And these nodes are responsible for managing these objects. They're responsible for keeping a database of which objects are active or inactive, and which objects exist. And in our system, these nodes are split into multiple shards so that they're responsible for different sets of objects. And that's the key scalability feature in our system. So how do we achieve privacy? So what is a chain space smart contract? So in our system, a smart contract has two aspects to it. The first aspect is the user side, or the execution side of it, and the second part is the checker side, which is executed by nodes on the blockchain. So the execution part of the smart contract allows users to create transactions. So for example, if it was a wallet smart contract, and that user wanted to send money, it would allow them to create a transaction sending money from person A to person B. And then they would send that transaction to the node, and that node would check, using the checker part of the contract, that transaction is a valid transaction. So for example, it's sending the correct amount of money. So for example, if it's sending 6 coins when the balance of that account is only 5 coins, then that would obviously be an invalid transaction and the checker would fail. So the first step is the user has to download the smart contract. Then the user has to execute that smart contract to create a transaction, which would then send that transaction to the node. The node checks that transaction is valid and then updates its database of inputs and outputs. Now, we did it this way to achieve privacy by design. Because what this allows us to do is smart contracts can actually have different parameters for the execution side and the checker side. Because you might not necessarily want to give all of the information used to create that transaction to the person who's checking that transaction. So to give you a concrete example, when you do online banking and you want to send money to someone, you obviously need your username and password and your authentication information. And then you use your online banking account to send money to some other bank account. And obviously, for your recipient to check that they've actually received that money, they don't need to know your username and password. They can just log into their bank account and check that they've actually received the money. So that's the kind of same idea here. If you want to send money to someone, obviously you need to know your secret key or password to actually be authorized to send that money. But to check that that money has been actually sent correctly, you obviously don't need to know someone's private key. But that's basically exactly how Bitcoin works. But what we wanted to do was to support more generic kinds of smart contracts like this. So one of the applications that we developed, for example, was an e-petition system, an anonymous e-petition system. So traditionally, if you want to sign an online petition using change.org or whatever, you have to give that website or petition creator your identity, as in you have to prove to them that you're a real person. So you have to give them your address, your name, etc. And that's not very good for you from a privacy perspective. So what we tried to do was to create an anonymous petition system that can still validate that the people who are signing a petition are real people, which means that you can sign a petition anonymously and people can be sure that the people who signed this petition are real people without knowing who those people actually are, which sounds a bit like magic, right? How do you know that a petition has been signed by a real person without actually knowing who that person is? So what we did, what would happen is that when the user creates this transaction, they would provide a special identifier or a secret to prove that they are a real person. And the node and the user would generate what's called a zero-knowledge proof, which basically means that you can prove to someone that you know something without actually showing what that thing is. So I can prove to you that I know a specific number without telling you that specific number using some fancy cryptography called zero-knowledge proofs. So similar concept here, it allows a user to prove to a node that they are authorized to sign a petition, or they are actually a citizen of a specific country, authorized by its government or issued a passport, without actually revealing that passport or identity or who they are, using zero-knowledge proofs. So how do objects map to shards? As in, which shards manage which objects? So the smart contract itself can decide which shards manage which objects. And this is kind of interesting from a regulatory perspective, because if you wanted to set up a system, for example, where some shards are based in Europe, for example, and some shards are based in the US, and you didn't want, for example, for regulatory purposes, for that data to be handled in the US, then you can instruct that smart contract to only use shards in the EU, for example. Finally, I'm going to talk, well, not finally, but I'm going to talk about scalability. So, to achieve scalability, we split up the blockchain into multiple shards, as was discussed previously. Which basically means that we split up the actual state of the blockchain to different groups of people. But that creates a problem, which is called the train and hotel problem. Let's suppose Alice wanted to go to a travel agent and book a hotel room and a train seat at the same time. And let's suppose that shard 1 is responsible for the hotel system and shard 2 is responsible for the train booking system. So now the travel agent has to speak to both of their shards to book that hotel room and book that train seat at the same time. But what if Bob comes along and submits a transaction trying to book the same hotel room in the same shard at the same time? Which transaction should go through, right? So you might end up in a situation where the travel agent sends both of those transactions, but only one of them go through. Only the train receipt transaction goes through. So Alice has ended up with a train booking, but doesn't have anywhere to stay. And that's a problem, because then Alice has spent money paying for something that she doesn't want. So what we're trying to achieve here is something called atomic commit. Ideally, what would happen in this situation is that either both of those transactions go through, or none of them. As in, we wanted to make it possible so that either Alice ends up with both a train and hotel booking, or nothing. So we can't end up in a situation, or we don't want to end up in a situation where only half of the transaction goes through. We want everything to go through, or nothing. And this is called atomic commit. So we've developed a protocol that achieves this by allowing shards to communicate with each other to agree on which transactions should go through and which transactions shouldn't go through, so that transactions should only be processed atomically. This is called the sharded Byzantine atomic commit protocol, and it essentially operates in two phases. And essentially what happens is that when someone sends a transaction to the system, all of the objects that transaction is using as inputs get locked, so that no one else can use them while the transaction is happening, and then they get unlocked at the end. Now, our SBAC protocol relies on some form of Byzantine fault-tolerant protocol. You can see there in the boxes that say BFT. Now, it doesn't matter specifically what BFT protocol is used. You could, for example, use a blockchain and proof of work, or you could use a more traditional Byzantine fault-tolerant protocol, like practical Byzantine fault-tolerant. But the protocol itself is agnostic to what Byzantine fault-tolerant protocol you use. And the key thing with this protocol is that only the shards that are managing the objects that are relevant to the transaction that have to do any work. And those shards can work in parallel, so the system is scalable. So what are some of the security properties of this system? So in chain space, you can say that there's two types of shards. There's honest shards and there's malicious shards. And the honest shard is one that's actually processing transactions correctly and doesn't have a majority of malicious adversaries. Whereas a malicious shard has been compromised by malicious participants that aren't processing transactions correctly. We guarantee 4 security properties. The first one is transparency. And what that means is that anyone can authenticate or verify the entire history of every single transaction that has happened by looking at the blockchain to audit the blockchain and to verify that the transactions are actually being processed correctly. Second one is encapsulation, which means that a smart contract can't actually change objects or manipulate objects that are created by other smart contracts. So a smart contract can only deal with objects related to itself. Thirdly, we guarantee integrity, assuming that a shard is honest, which means that if a shard is honest, then only valid transactions will be executed atomically. But if a shard is dishonest, then we guarantee something called non-repudiation, which means if a shard misbehaves, then that misbehavior is detectable and something can be done about that. Finally, let's talk about performance. So we implemented a prototype of the system. It's on GitHub, so you can check it out if you want to. And we also deployed and tested the system on Amazon Web Services. For the Byzantine fault-tolerant protocol, we used a library called BFT Smart. And we've also created a smart contracts environment in Python that allows people or developers to easily create contracts. The first thing we measured is the throughput. How does the throughput change as you increase the number of shards? So you can see, for example, with 3 shards, we can handle about 70 transactions per second. If you increase that to 14 shards, it goes up to about 350 transactions per second. So you can get about 20 transactions per second more per shard using our implementation. If you probably made our implementation more efficient, you can probably get a bit more. But the key takeaway here is that we have a linear scalability property. So the more shards you add, the higher the throughput. Secondly, how does the throughput change as you increase the number of nodes per shard? Because obviously, if you only have 4 nodes per shard, then it's not very decentralized. You can just corrupt 4 nodes, or actually, you only have to corrupt 2 of those nodes, actually. So, if you increase the number of nodes per shard, how does the throughput change? So, if you only have 4 nodes per shard, you get about something like 70 transactions per second. If you increase the number of nodes per shard by 10 times to about 40, you only get a modest decrease in throughput to about 50 transactions per second. So you can easily scale this up to many nodes per shard without having a big hit in throughput. Thirdly, how does the number of input objects per transaction impact the throughput? Because obviously the more input objects that you have in a transaction, the more communication that needs to be done between shards to make sure that the transaction should go through. Initially, if you increase the number of inputs per transaction, the throughput goes down, but it levels out after a certain point, and that's because there's only a maximum number of messages that shards have to send between each other. So, for example, if there's 5 shards, then they only have to communicate with 4 other shards each, no matter how many inputs there are per transaction. And finally, how does latency looks like? So if you have the purple line, which shows what the latency is for 100 transactions per second, you can see there's an 80% probability that that transaction will be processed in under about 600 milliseconds. So what else is in the paper? So if you want to read the paper, you can check out the link below to read the full paper. We also mention other things in the paper, such as other applications and some benchmarks for smart contracts. So in conclusion, we talked about how to create a distributed ledger or blockchain that scales linearly by employing sharding. And secondly, we talked about how to create a distributed ledger that supports privacy-enhancing technologies by design so that people can have privacy-preserving smart contracts. What is some potential future research work that can be done here? So first of all, we haven't mentioned in the paper how to actually recover from shards that are malicious. So if a shard becomes corrupted by some adversaries or becomes malicious, and how do we recover from that? There's a lot of solutions to this, but we didn't actually talk about this in the paper. And also, how do you actually bootstrap the nodes in the system in a decentralized way? Because obviously you need some kind of way to assign nodes to shards in a way that it can't be corrupted. So you can use as OmniLedger does, use a bias-resistant randomness protocol. But the system itself isn't dependent on how it's bootstrapped. We actually specified in the paper that it could be managed by a shard management contract. So it's up to you how you want to do that. And finally, how do we actually incentivize the nodes? So we can, for example, add transaction fees and make it so that nodes earn transaction fees as they process transactions. Thank you. I think we have a fireside chat now.
Thank you very much, Mustafa, and Philip as well. That was really fascinating. So, we have Philipp up, and perhaps we'll take some questions and have some discussions. I think there's there's a third microphone for you, and I think our friend over here has another microphone, so that with the live stream that's currently going on Facebook and YouTube, we can have your questions mic'd up rather than us having to repeat your questions. So, firstly, could I just have a general understanding of who found that really informative? Did we find it really, really clear and crisp, and we got the concept? Great, fantastic. So, I'd like to ask a question firstly, and open it after that. Mustafa, Philip, we were having a chat before we began this evening, and we were trying to establish like a definition of sharding, which I think is the key innovation that you're both engaging with. Now, I mentioned from my understanding of sharding that it was a kind of trade-off between the number of nodes that hold your data on the blockchain versus the speed and efficiency with which, if you have a smaller number of copies, so let's say there are 20,000 Bitcoin nodes, maybe you don't need 20,000 copies of your data on the blockchain to validate it so that you're happy that it's not going to be corrupted or cartelled or gamed. So we have a smaller number of nodes storing our data. What is it that you think that allows sharding to be as secure as a linear serial blockchain where every node holds the same data in the full blockchain?
I mean, so initially you would think that actually there is kind of a trade-off between security and scalability, and I think that's always existed in the blockchain world, whether it be sharding or Lightning Network or bigger blocks or whatnot. Now the challenge with sharding is that if you're sharding the state of the system, you're also in a way sharding the security of the system. Because the reason why having a single blockchain is so secure is because it's hard to corrupt the blockchain if there's loads of nodes in it, or lots of mining power in it. But if you start splitting up that mining power, or if you start splitting up nodes in the blockchain, then you're also making it easier to corrupt one specific one specific shard. But of course there are solutions to that. One of which I think is in the OmniLedger paper, which is to have a bias-resistant, random way of assigning these nodes to shards. Another way another technology that has been looked at recently, specifically with Ethereum, is this idea of fraud proofs, which means that if a specific shard is malicious, as long as there's at least one honest person monitoring that shard, they can generate a cryptographic proof that that shard was misbehaving and send that proof to everyone else to prove to them that a specific transaction in that shard is wrong.
So you can have shard whistleblowing. So you've got the WikiLeaks of shards. So
that's how I like that.
Yes, we've got that. Okay, so you can create the shards, and then at each point you can monitor their performance and see whether they're actually being honest or malicious. So Philip, what would be your response to that notion?
Yeah, I like that notion very much as well, and I can't really add much. I think that, since blockchains, they publish their data on this public bulletin board, right?
Yeah.
You can always, an observer can always see, okay, something went wrong, and now we take that proof, and there can be mechanisms to punish the misbehaving nodes. That's where then these incentive mechanisms that Mustafa briefly talked about come in.
Cool. Okay. So let's open it to the floor. Who has a question or something they're interested in this set of talks? Raise your hand. The lady down here in the Burberry print.
Thank you. I have a question for Mustafa. So you mentioned that in order to send a smart contract, you need to set up a password or a key. What happens if you have to send a few contracts in a day? and you have to remember all these passwords. You will end up saving those passwords somewhere. Is that secure to?
Okay, so when I say password, I don't literally mean password. I mean a private cryptographic key. So in order to send a transaction in Bitcoin today, for example, you have to have like a secret to prove that you actually own the account or the address that you're trying to send that transaction from. And you don't have to, obviously you don't have to remember that secret. That secret is actually just stored on your computer. But that does create some challenges. So for example, if you lose your computer, then you lose all your Bitcoins, or you lose all your money, or you lose all of your ability to interact with the smart contracts that you authorized to interact with. So this is still a big problem in this research space, and it's basically called the key management problem. How do you actually allow users to manage their keys securely, and in a way that doesn't allow them to lose money if they lose their computer, for example. Also, because if you just make a backup of it on the internet, then if someone hacks your Dropbox account, for example, they can steal your wallet unless you encrypt it. So what a lot of people do is just store their coins on online centralized exchanges like Coinbase, etc. Obviously, the flaw there is that if those exchanges get hacked, then your money gets hacked. You can also use what's called a hardware wallet, which is like a piece of hardware that actually has your private keys on them. And also, what a lot of wallets do nowadays, like Electrum, for example, they generate what's called a seed, which is basically 12 words that you have to remember that you can reconstruct all your private keys with. So even if you lose your wallet, as long as you remember those 12 words in your head, then you can reconstruct all your private keys automatically just by typing them into the program.
Yes, you can make it the 12 words of your favourite song or your favourite poem, but of course they have to be 12 words that aren't very well remembered by anyone else, otherwise they'll be able to guess them.
Well, you can't actually choose those 12 words. It's generated randomly.
I know you can. You on Electrum.
But that's not very secure. If you choose,
yeah, well, that's the thing. If you have your own, or if you use a random seed.
Use the words that the systems provide you with, because they guarantee that these are randomly chosen and that this is secure, right? Because as soon as the words, like, for example, if you take a favorite poem or something like that, then the chances might be actually quite high that another person also has the same idea to use the exact same poem. And then suddenly you end up with the same private keys. And then if that person is malicious and he finds out, then he can steal all your funds from your account, right?
Yeah, and don't use your favourite line from a poem or song and just change all the L's to ones, because I'll guess that one too.
Right. Don't use lead speak.
Anybody else? Who's next? The gentleman at the front in the Star Wars t-shirt.
Right. Both of our presenters mentioned crypto kittens, right? How your system solve crypto kittens problem. So multiple users from all the shards try to transact to a single address in a single shard.
So in the chain space context, each kitten would have its own object. So it's not like you interact with one contract. You interact, people are interacting with lots of different objects. And so like an object is a state of concurrency. So each kitten is just one object. So you can trade as many kittens as you want, really.
Same or similar in OmniLedger, you have this atomics protocol, right, which is managed by the client. And then when you want to trade a kitten, you just create the corresponding transaction that allows you to do that. And then you send it to the system, and then the system takes care that everything is executed atomically and that the trade goes through in a secure way.
Well, maybe that would be also a good point to highlight some of the trade-offs between OmniLedger and ChainSpace. So OmniLedger is specifically focused towards payments context. So in contexts where there's only like one user who's authorized to make a transaction from whether it be a kitten or a bank account. whereas chain space is more targeted towards generic smart contracts, where anyone is supposed to interact with an object, for example, an unbooked train seat. But the trade-off is that in OmniLedger, the consensus protocol for locking happens on the client side, whereas in chain space it happens on with the nodes. So there's a lot more communication overheads in chain space with the nodes, whereas in OmniLedger that's pushed back to the user side, so it's a bit more efficient.
But at the same time, I think that these are like actually complementary approaches that actually it would be very interesting to look into an approach that actually combines OmniLedger and chain space.
What would that look like, gentlemen?
Well,
do we have
that's an open
moment of consensus on stage?
That's an open research question.
Okay. But which aspects of each would you be interested in combining in a strong whole?
I mean, you can combine the bootstrapping aspect of OmniLedger with chain space. So OmniLedger has a way to bootstrap shards in a decentralized way, which is not something that we mention in chain space.
Okay, so I was looking at different kinds of decentralized storage myself, and I had a question about. I mean, shards are quite new to me, but my notion was okay. You can have multiple different channels in parallel, producing different transactions or smart contract clauses and so on. But how about redundancies? Actually, there's a potential, right, for having a couple of shards doing exactly the same thing. So instead of having, as you say, a malicious shard which then maybe has a whistleblower, perhaps you could have 2 or 3 shards doing the same set of transactions. So you have the opportunity so they can't game that notion that they're the only potential point of failure. Does that make sense to you?
I mean, I get the idea, but from a technical perspective, I'm not sure there's a difference between having 2 shards with 10 nodes in it each and having 1 shard with 20 nodes in it. So I think your redundancy can be achieved simply by adding more nodes to the same shard. You don't necessarily need to have different...
No, but in your graph, there was that trade-off. So from 4 to 10, the efficiency was increasing. Then you had a plateau to 20, and then it dropped to 40. Now, you said yourself that a single shard with 40 had an acceptable level of decrease in performance. But how about 2 of 20 instead? I noticed that on your graph.
But I mean, if you have 2 of 20, when you make a transaction to an object that those shards control, then you're going to have to talk to 2 shards instead of 1. So I think that trade-off is still there, even if you have 2 shards.
Interesting.
So a nice thing where this kind of redundancy comes in is, for example, when you fly in an aircraft, right? Then there are multiple redundant systems who are doing the same thing, and then you basically have, like, let's say 3 systems who are implemented in a different way, who run on a different hardware, and then they at the end there is a voting saying, okay, if like one system fails, then and 2 of the others agree, then we go with these 2 because the probability that all 3 of them are incorrect or 2 of them are incorrect is not as good as if just one of them is incorrect. So you can transfer this also in a similar way, for example, to smart contracting, where you have like 3 contracts which were written by independent 3 people in 3 different smart contracting languages, and then because it's very right in most of the time when we hear some security failures in smart contracts, then there is a bug in the smart contract. Now, when you have like this redundancy with 3 contracts that all do the same thing, the chance that a bug affects all 3 of them is not as high as if it just affects one of them and takes it down. So you can somehow get this redundancy also in the smart contracting way, but you of course have an overhead.
So like a
This
kind
added security.
like a kind of proofreading or you know.
In some sense, yeah.
So taking the DAO as an example, or different wallets or smart contracts that have been corrupted, if you had different people authoring the same function in slightly different ways, but doing the same thing, then you might prevent exploits and workarounds. And because the code is open source in blockchain to a great extent, then you have the opportunity for people to go through with a fine-tooth comb who might be more intelligent than all of us put together.
The particular hard challenge in blockchain systems, like auditing blockchain systems and finding bugs in there, is that like in classic software systems you have bug bounties, right? And you give people money for finding bugs. But now if you find a bug in a cryptocurrency, then cashing out is often much more valuable than like getting the bounty, which is often a fraction of the percentage. So you can, if you find a bug in Ethereum, then you can make millions, right? And there won't be any bug bounty that can give you millions for one single bug. So that's like really a hard problem where more research is necessary to solve that.
So, in other words, look for the errors in the code, make a lot of cash, like the guy that did the DAO. As they say, the DAO giveth, the DAO taketh away. Long live the DAO. Anyway, with that, thank you, Philip.
Thank you.
Thank you, Mustafa.
Thank you.
And thank you from me, I'm Lorenzo Mefsit. Thank you to Binary District for hosting us tonight, and I think there are lots of snacks and drinks over there at the bar. The gentleman will be here for you to grill them on sharding and different kinds of crypto security to make sure you stay safe, and anything else they're here to explain. Actually, there's a couple of colleagues, I think, it was from the project as well. And we'll be here all night, folks, so have a good one. And remember, the blockchain revolution is for you, okay? Have a good night. Have a drink. Thank you so much. Thank you, gentlemen. Thank you.